Hi everyone, this is a presentation on related rates for MAT213 brief calculus. In this section we're going to take a look at functions that are actually functions of time. That's again what it means up here where it says time dependent. Some examples can be cells of an item that depend on seasons. Again, think things like turkeys or Christmas trees or pool toys. Or a population of animals in the wild. For example, the population may be time dependent and it may increase, say, in the springtime and decrease in the fall. Time is often in these types of mathematical models, and it requires that we use implicit differentiation with respect to time when we find derivatives. So this is very similar to what we did in the previous section. The only difference is that we're going to have functions of time that are both x and y. They're not just going to be, say, a function where we have y in terms of x. Okay, so this is a third variable that's going to be in the, it's going to be the variable that we take a derivative with respect to. Okay, here's the first example. Okay, suppose this is an example without any context whatsoever. In this example we have x and y as functions of t. Okay, and we want to differentiate this on both sides implicitly with respect to time. They also give us some values. They tell us in this scenario x is 2, y is 3, and the rate of change of x with respect to time is 13. Notice there are no units in this problem because there is no context to the problem. They are asking us to find dy dt at the instant when the variables and the rates have all of these values. So again, because x and y are both functions of t, we need to use, first of all, the product rule for the first term here, and then for each variable we're going to use the chain rule. What that means is every time you differentiate an x or a y, you're going to have a dy or a dx dt attached to it. Okay, so let's take a look at this first term, okay, the xy squared term. We're letting the u value be x and the v value be y squared. We need the derivative of both of those terms. So if I differentiate x, the outer function is going to give me a 1, and the inner function gives me dx dt. If I differentiate y squared, I'm going to get the derivative of the outer function being 2y, and the derivative of the inner function being dy dt. That is an application of the chain rule. Now if you remember how product rule works, it's the first term times the derivative of the second plus the second times the derivative of the first. So I'm going to use the values I created up here and plug them in. So I get x times 2y dy dt plus y squared times dx dt. Okay? Remember, there was more to this function than just that first product term. Okay, I have a y on the left-hand side and then an x squared plus 17 on the right-hand side. So I'm going to continue differentiating. Please notice this first part here is the stuff from the product rule. This is the derivative of y with respect to t. And on the other hand, on the other side of the question, this is the derivative of the x squared with respect to t. 2x is the outer derivative and dx dt is the inner derivative. Then I'm going to take the given values that I got for x, y, and dx dt and plug them in to this expression. So 2 goes in for x. Okay, you can see that's the red highlighted values. Okay, the y is the purple highlighted values, and the yellow highlighted values are dx dt. Okay, then if I do a little bit of arithmetic, I'm going to get 12 dy dt plus 117 plus dy dt equals 52. The only thing I need to do is get all the terms with dy dt on one side. So I'm going to subtract the 117 from both sides. Okay, that gives me 12 dy dt plus 1 more dy dt equals negative 65. Factor out dy dt. Okay, it goes in this term 12 times, this term once. Okay, that gives me 13 dy dt. And then divide both sides by 13. So dy dt is negative 5 in this example. Okay, so to go back up, okay, the calculus is pretty much just at the very beginning of the problem where you're actually taking the derivative with respect to time, and all of the steps that come afterwards are all algebra steps. In general, if you want to solve a related rate problem, okay, the first step is similar to solving any applied problem, and that's identify all of your given quantities as well as those that you want to find. Okay, the quantity you want to find will probably be in the form of a question. Okay, and it's usually somewhere near the bottom of the problem. Draw a diagram if you actually have a physical situation that you're trying to model. That's really helpful. And then you need to come up with an equation that relates the variables in the problem to each other. This might be the equation for the area of a geometric shape, the volume of a geometric shape. It could be the Pythagorean theorem. It could even be revenue is price times quantity demanded. Okay, so you have to be aware of how these variables relate to each other. Once you come up with an equation, you're going to use implicit differentiation with respect to time to differentiate both sides. And the last step is to solve for the unknown rate of change that you're interested in by plugging in all the known variable values that were given to you in the problem. Okay, and as I said, there's a fair amount of algebra in actually coming up with a numeric answer. Let's take a look at a problem that actually requires us to draw a diagram. Imagine that we have a 50-foot ladder placed against a large building. The base of it is resting on an oil spill, so it's slipping away from the building at a rate of 3 feet per minute. Yikes, okay? That must mean the top of the ladder is sliding down the building, okay? And what they want us to answer is, what is the rate of change of the height of the top of the ladder above the ground at the instant when the base is 30 feet from the building? Okay, so they're asking us, again, how fast is it sliding down the wall? I think this scenario definitely requires a drawing, so let's do that. Okay, here's a picture. The Y here that I've called Y is the building. Okay, I'm calling it Y because usually vertical distances are called Y. Okay, here's the ground. That's a horizontal distance, and I'm calling it X because that's familiar. And we're given that the base of our ladder, which is this diagonal 50-foot distance, okay, is 30 feet away from the building. So I'm marking that on my diagram. Now, what type of an equation relates the three sides of a right triangle? Right? We're assuming our building and our ground meet at a square corner here. So this is a right triangle. And again, you might remember that these are related by the Pythagorean theorem. Okay, if I square each of the legs of this right triangle, the y and the x, that should be equal to the square of the hypotenuse, which is this long diagonal side. You have to remember, this is not going to change. The 50-foot ladder is always going to be 50 feet. Okay, so this is the relationship of the three sides of the triangle. X squared plus y squared is 2,500. Next, we have to come up with an equation that relates the rates of change of these quantities. Okay, so we know the ladder is moving with respect to time, both in the x direction. If you look back at this diagram, you can imagine as the ladder slides away from the bottom of the wall, the top of the ladder is going to slide down the wall. Okay, so both x and y are changing with respect to time. So I'm going to differentiate x squared with respect to time. That gives me, using the chain rule, I'm going to get 2x for the outer function, dx dt for the inner function. Same thing with y squared. The outer function gives me 2y, and the inner function gives me dy dt. Since the right-hand side of this equation is a constant all by itself, it's going to differentiate to give me a 0. Okay? Now what I'm going to do is substitute the values I was given. And we were given a value for x. We said we knew the ladder was 30 feet from the base of the building, and we knew it was sliding away from the building at the rate of 3 feet per minute. Okay, so that is dx dt. We don't have a value for y, and this equation has a y value in it. The dy dt is the unknown we're going to solve for. So how would I be able to get a y value? Well, I can go back to the Pythagorean theorem and plug in the x value they gave me. Okay, so I'm plugging in 30 for x, and I'm going to solve for y. You can see this gives me a 900 when I square it, and then when I subtract it from both sides, I get y squared is 1600, and y is the positive square root of that 40. So when that ladder is 30 feet away from the base of the building, the top of the ladder is 40 feet above the ground. Now I can finally plug in all my known values in my derivative. Okay, so x is 30, dx dt is given as 3, y is 40, and then I just have to simplify. This quantity over here gives me 60 times 3, which is 180. This gives me 80 dy dt. And I just need to solve for dy dt. I'm going to subtract the 80 dy dt from both sides. You could also have left this alone and moved the 180 over, and it would have become negative. And then the last step is to divide both sides by negative 80. So I get a value for dy dt as negative 2.25. But since this was an applied problem, it has units. And the units for the rate of change are going to be the same units you see here. Okay, the y units were in feet, the t units were in minute. So I'm going to have the same units that I had on dx dt, namely feet per minute. So the correct answer to the problem is that as the base of the ladder slips away from the building at the rate of 3 feet a minute, notice this is positive, that means the distance from the building is increasing. The top of the ladder is sliding down the building, that's why this is distance above the ground, is decreasing at a rate of 2.25 feet per minute. Okay, it's important to pay attention to both the units and the signs of these derivatives, okay, in order to correctly explain what's happening in an applied problem. Let's take a look at another problem. This was an extra credit problem on your last exam, you might remember it. Suppose we have a slick, an oil slick on the surface of the ocean or a lake. Okay, you might have some experience with things like soap slicks or whatever spreading on the surface of water, and you know as the radius of the circular slick increases, the area is going to get bigger, so the circle is going to get larger. So essentially this problem's saying it spreads out so that as the radius changes with respect to time, so does the area. We know the radius change is 2.1 meters per hour. Again, notice the units. Okay, we're measuring distances in meters and we're measuring time in hours. They want us to find the change of the area with respect to time when the radius is 21.2 meters. So again, we have our drawing, okay, with our radius filled in. We need to figure out an equation that relates area of a circle to a radius, and that is area is pi times the radius squared. The next step is to differentiate both sides of this implicitly with respect to time. Again, area is going to increase with time, and so is radius. So here is the differentiation. Again, the derivative of area, the outer function, gives me a 1. The derivative of the inner function with respect to time gives me dA dt. Pi is just a constant. It's like a coefficient in this equation. So I'm just going to pull it through. Okay? And then I'm going to differentiate r squared with respect to time. So the derivative of the outer function r squared gives me 2r. And the derivative of the inner function gives me dr dt. All that's left to do is to plug in the given units. Since this is already solved for dA dt, I don't need to do any algebra to isolate that rate. So I'm going to approximate pi with 3.14. I'm going to plug in 21.2 meters for the radius and 2.1 meters per hour. I'm pointing out, note the units, okay, so you can kind of see what the final units for dA dt should be. Pi is dimensionless, no units. The radius is in meters, and the rate here of change is in meters per hour. Notice the 2 meters in the numerator multiply together to give you meters squared per hour, which is the right unit for the rate of change of an area. Okay, so our final answer is 279.6 meters squared per hour as the rate of change of the area of this oil slick. That might be useful to any first responders who are coming to try to clean up the slick. They'll have some idea as to just how big it will be and how much material they need to bring with them to contain it. Here's our last example, and this is a business example. A company is increasing production of peanuts at a rate of 50 cases per day. Now they said increasing, so we know that this rate, and again the word per gives it away, and so does the word rate here. This is a positive number, and it's measured in cases per day. All the cases produced can be sold, and here's the demand function, the daily demand function. You might remember this from previous examples where P is price, Q is quantity demanded. Okay, in this example, the quantity demanded is also the quantity we're going to produce and sell. Okay, and they're telling us Q is the number of cases produced and sold, and P is the price in dollars. Okay, both of these quantities change daily. Okay, so essentially we want to find the rate of change of revenue with respect to time when the daily production, okay, production is going to be a Q value, is 200 cases. Okay, so they're asking us to find dr dt, but we don't have a revenue function. We need to build one. Okay, we're going to build a revenue function from the given demand function by multiplying our price by our quantity demanded. You might remember from our class sessions my banana example where I said, let's suppose you want to buy 8 bananas, that's the quantity demanded, and they're 10 cents each. Okay, what would be the revenue somebody would gain from selling you the 8 bananas? That would be 8 times 10 cents or 80 cents in revenue. All right, so this is the way you want to build your revenue function. Just take your quantity demanded and multiply it by your price function. So here's my Q, and I'm multiplying my expression for price. And you can see after I distribute the Q, I'm going to get 50Q minus Q squared over 200. Next, I'm going to differentiate this expression, this equation rather, implicitly with respect to time. On the left-hand side, I'm going to differentiate r, that gives me a 1, and then take the derivative of the inside function, because I'm using the chain rule, because r is a function of time. That gives me dr dt. And then I'm going to differentiate 50q with respect to time. 50 is a coefficient, it just comes through. Q to the first differentiates as 1 for the outer function, and dq dt for the inner function. If I differentiate q squared over 200, you have to think of this 200 in the denominator is the same as 1 over 200 as a coefficient, so it's just coming along for the ride here. Here's the derivative of the outer function q squared. It gives me 2q, and here's the derivative of the inner function dq dt. I'm going to do a little bit of arithmetic to clean it up. And I'm going to cancel out a 2, divide out a 2 from the 2q and the 200. So this term becomes 1q over 100, or 1/100th q. Everything else stays the same. I'm highlighting the quantities that I'm going to plug in given values for. I was given that dq dt, that is going to be the rate of change of production. Okay, and again, if you go back to the beginning of the problem, you can say they're increasing their production at the rate of 50 cases per day. So I'm putting in 50 for dq dt, Okay, and my Q value was when my production was at 200 cases per day. So I'm putting in all of the given values. Okay, my revenue, if you think about it, is going to basically be in dollars per day. Okay, so let's take a look at that. Okay, I'm getting 2,500 minus 100, or $2,400 per day. Okay, again, it's really important in these problems to use the correct units and the correct sign on your rate. Here, my revenue is increasing, okay, and it's increasing at the rate of $2,400 a day when I make and sell 200 cases of peanuts, and that production rate is increasing at the rate of 50 cases per day. Okay, hopefully you enjoyed this little presentation, and if you have any questions, please don't forget to email me.